In this subsection 6.2.2, we'll talk about orthogonal projections. We'll begin with an example in R2 space, where we have a vector u in R2, and we want to decompose it into two terms. We want to decompose u into one term along the vector A and one term along the vector that is orthogonal to A. To perform this process, we will find u in the R2 space, and we assume that we have q, the initial point, where we can have the vector A and q shares the same initial point as u. The idea is that we are going to drop from the tip of u onto A, and we'll call this projection W1. Basically, W1 is a projection of u onto A. Now, by only using W1, we could only explain u along the direction of A. There is some more residual. And because we have projected it perpendicular to it, this is the residual, and we can simply say u minus W1 would be this residual vector, and we call it W2. And simply, u is equals to, if we move W1 to the right hand side, is W1 plus W2. In other words, we have managed to decompose u into two vectors. And these two vectors, W1 and W2, are orthogonal to each other. And W1 is a scalar multiple of A, because in this example on top, A is a long vector and W1 is a smaller version of it, but they are pointing to the same direction. We have other examples where now u is a long version of the previous example and W1 is a longer version of A, although they are still in the same direction. And in the last example, where we have u turning anti-clockwise, and now we are projecting u onto as A, but now W1 is a negative scaled version of A. You will realize that we like to decompose vectors into orthogonal bases. We'll revisit this term orthogonal basis later on, but you are very familiar with something called the standard basis. The standard basis of Rn is nothing but a vector, a set of vectors E1, E2, up to En, where this small little n is the same as this. And in our R2 case, these two vectors are 1, 0, 0, 1. The first column is E1. The second column is E2. And for the R3 case, the first column is 1, 0, 0. Here we use the row representation or the R3 tuple, or alternatively we have written it as a column vector, and so on. The use of orthogonal basis is also done for complex numbers. The complex numbers is sometimes drawn in the complex plane, where x here is the line of the real number line, and y is the imaginary number line. And they are orthogonal to each other. The first coordinate of a complex number is for the real part, and the second coordinate for the imaginary part. Or sometimes we say z, the imaginary number, is equals to some real number plus, and in this case the word I here stands for the imaginary axis, times the value b, where the b is the value here. If you need a revision, here is a quick link to complex numbers. In this slide, we'll discuss the projection theorem. The projection tells us that a vector u can only be expressed in exactly one way when we have w1 and w2 are orthogonal to each other. So this is very nice. It means that u has a unique representation when we decompose u into orthogonal vectors. There are various names. If we project u onto A and we get w1, sometimes the name or the notation is called orthogonal projection of u onto A. Sometimes we call this the vector component of u along A. And sometimes we write it as w1 is equals to the projection of u onto A. What about w2? w2 is orthogonal to A. So w2 is sometimes also called the vector component of u that is orthogonal to A. How do we compute w2? Well, w2 is simply u minus w1. And then we can use the clearer notation, which is the projection of u onto A as the representation for w1. How do we find w1? w1 is equals to the projection of u onto A. The equation is u dot A divided by the norm square of A multiplied by A, the vector. We must always remember that w1 is a vector, and it is a vector in the same direction as A. It is different to A because it is the vector component of u. That means how large it is of u along A. Actually, there's another easier way to see this. It is nothing but this value. This is the vector component value of u on A. What I mean is this length, the norm of w1, this length, can be represented as cosine theta is equals to the adjacent over the hypotenuse. Then the adjacent is the norm of w1, and the hypotenuse is the norm of u. And therefore, w1, the length of along A, is equals to norm of u cosine theta. Now, because we actually want to get w1 and not just simply the norm. We know that we are interested to find the direction of A. Now, if A is not a unit length vector, what we can do is to get a unit length vector from A, we divide by its norm. And we can continue to say that now we have this direction, we multiply by the length. Now, to get from this equation to this equation, all we need to do is to multiply the top and bottom by the norm of A. We then recognize this part as U dot A. We collect the bottom and see that this part is equal to the norm of A square. And the last vector A remains outside. So now we understand how this equation, projection of U onto A, is this complicated looking expression here. What about W2? Remember, we say that W2 is equal to U minus W1. We substitute W1 here and we get U minus projection of U on A. And then we substitute this complicated looking expression here and we get U minus U dot A divided by the norm of A square multiplied by vector A. We wish to remember that W2 is a vector component orthogonal to W1 or orthogonal to A. Below, please try example 5 to project U, an R3 component, onto vector A. Once you have found that, then find the vector component orthogonal to A.